I'm Dr. David Mukai, and today I'd like to talk to you a little bit about earthquakes. I'm going to go over two earthquakes that I went to observe damage in New Zealand. We'll head out to my garage, and then I'll show you a demonstration about how buildings respond in earthquakes, and then I'll end with some of the work I'm doing right now in Japan. So, let me talk about these two earthquakes in New Zealand that I went to look at the damage after the earthquakes. And so these two earthquakes, let me get out of the way there. These two earthquakes happened in 2010 and 2011. And the first one on the left here, you can see that's where the fault was. It's very near to Christchurch. I happened to be working at the University of Canterbury in Christchurch at the time. And it was a very large earthquake. And then in 2011, there were a whole bunch of aftershocks, which you can see on this right here, and then ending up with a very large aftershock in February of the next year. And so if you compare these two earthquakes, the first one was much larger in terms of energy. It was a 7.1 earthquake. The one in February was a 6.3. But the larger earthquake had no deaths, no collapses of tall buildings. There was a lot of quicksand or liquefaction and severe damage to brick buildings and about $4 billion of damage, which is quite large for a small country like New Zealand. The earthquake in February, which was basically an aftershock, was 6.3, and it's a log scale, so almost 10 times less energy, but it resulted tragically in 185 deaths. Most of those were in two tall buildings that collapsed and others that were damaged. There was also severe liquefaction or quicksand, and again damage to brick buildings, and this time $12 billion in damage, and they're still recovering from that. Let's look at some pictures from that first September 4th earthquake. And so here on the left, you see here's the center line of a road. And right here, right in front of where we're walking, is where the fault was. And it shifted. And so now you can see the left lane line of the road has shifted over to match the center lane line of a road. And a lane is about 10 feet wide. So that means the ground shifted about 10 feet. And so we walked over to there, and then we turned left and followed the fault line. It's kind of unusual to be able to see the fault of an earthquake rupturing the surface. And we followed it and went right through this house. So this is the front of the house here. And then it came out the back of the house here and headed out to a shed in the backyard. This is a bedroom inside the house where no one got injured. A kid that lived in this house, we were, a bunch of professors coming to look at the damage. He came and asked me if the earthquake aimed for his house, because you could see it in the distance for miles. Not quite miles, but until you couldn't see it. And it looked like it aimed straight for the house, and it went through the house. Here are some other pictures from that earthquake. A lot of brick buildings that were damaged. You can see this rubble of bricks here. You can see the end of this brick building coming out. You can see this chimney collapsed here. Down here, you can just see all the damage of brick buildings. A lot of buildings had little parapets on the roof, so you would have the roof here, and then a little short wall so people couldn't fall off the roof, and then these parapets fell over down into the street. There was extensive damage in this earthquake to brick buildings. And here's some pictures from that February 22nd earthquake, which had a lot more damage. And I was no longer living in New Zealand. I was no longer working there. And but I got invited back to go examine the damage with the Architectural Institute of Japan. And so in this top row here are all these experts from Japan that I traveled with. I met them in New Zealand. They flew from Japan, and we went and observed the damage. On the bottom row are the local people from New Zealand that helped us look at the damage. On the bottom left there, that's Stefano Pompano, and he's actually in Italy now. And here's some fire workers that would tour us around to help look. And then on the bottom two right here are graduate students. I just wanted to show this picture to show you that this kind of collaboration is international, and people from all over the world were there looking at this damage. And a lot of engineering work is international, and you collaborate internationally. So Italy, Japan, Malaysia, and New Zealand. Here is just some of the damage there. In the top row, this is a Copthorne Hotel, Camelot Hotel, and it was condemned. You see this little red tag here? That was on the door saying that building was condemned. And I couldn't find damage. Part of my job was to go around and examine damage. And so I went in there. I went to the rooms. It's a very luxurious hotel. And all these really fancy doors were all broken in. What they were doing was looking for any stranded survivors. And from one of these windows, I looked out. And this is a very famous landmark, this second picture here. The Cathedral Tower, which was collapsed and gone. It was kind of sad. It had survived that first earthquake, but not this second one. And I just couldn't figure out why this building was condemned. It got red tagged. You get a green, yellow, or red tag. I didn't tag the buildings. I was looking for damage with the Japan team. And I found out later that the building next door, which was severely damaged on the verge of collapse, was red tagged. And because this building was really close to this damaged building, it also got red tagged. I believe both those buildings have been demolished. This is a Forsyth Bar building on the bottom row here. And when they first went in there, they opened the stairwell, and then when they looked in the stairwell, all the stairs from, that looks like 20 stories, were all collapsed on top of each other in the stairwell. All the stairs had fallen down, and they were very worried because in the event of an earthquake, what you do is you go to the stairwell. They took out all the stairs, and they piled them here. I went and looked at those. And there were no bodies. It happened so fast that the stairs collapsed before people could get to the stairwell. But you can imagine opening the door to the stairwell and then looking down a shaft 20 stories. And so they had to evacuate people out of these windows. You see these broken windows. I think the stairs from the broken windows up were intact. And then from there below, there were no stairs. And so they got a fire truck ladder and then evacuated people out of the windows from that hotel. And this final picture here on the bottom right is a parking garage that is collapsed. And this is just what we were doing, going around looking at collapsed buildings and trying to understand why buildings here collapsed in this smaller earthquake, rather when no buildings collapsed in that larger earthquake. And so to help explain this, I'm going to head out to the garage and I'm going to show you a demonstration which I would normally show you in class, but we'll do it in the garage. And I'll explain the concept of earthquake response spectra. So I call this a snake pendulum, and I'm going to use it to teach you about response spectra for earthquake engineering design. So watch what happens. So why do you think that's happening? Let's look at it again from the side. so if you notice, the shorter pendulums, tick tock, tick tock, tick tock, go faster than the longer pendulums. Tick tock, tick tock, tick tock. So the shorter ones are going faster than the longer ones, and they're getting longer as you go back. And so watch again. And so the shorter ones are getting ahead of the longer ones, and it's causing that serpentine. Now, in an earthquake, what happens is that the ground moves. So I'm going to shake this back and forth, but what I'm going to do first is I'm going to shake it at this speed. Tick, tock, 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 tick, tock. You see how the short ones are moving? Now what I'm going to do is I'm going to shake it at the speed of the long one. Tick, tock, 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 tick, tock. And so I'm making the long ones go more. And so buildings are just like these pendulums. Depending on how tall they are, they'll shake at a certain speed. The shorter they are, the faster they'll shake, and the longer they are, the slower they'll shake. And it depends on how fast the ground moves, which buildings are getting shook the most. That's called a response spectra. Well, I hope that little demonstration made sense to you. So if you remember, when I shook the snake pendulum at the frequency of the short strings, then the short strings would move more. And when I shook the snake pendulum at the frequency of the long strings, then the long strings would move more. And there's a very similar thing that happens to buildings. And we're going to talk about something called response spectra. And so here are the response spectra for that first New Zealand earthquake. And so what we can do, we know how to take an earthquake record, put it into a computer simulation, and then depending on how tall the building is, we can see how much that building will move or actually accelerate. We really want to know the acceleration. And so what you see here on the bottom axis is like our strings from short to long. But what it is, instead of length of string, it's the period of the tick-tock of the string. But in this case, it's buildings. And as a rough rule of thumb, the period, the tick-tock of a building is about 1/10 of a second for every floor. So a 10-story building would have a period of about 1 second. A 25-story building, 2.5 seconds. A 1 to 5-story building, 0.1 to half a second. And what we have here in this black line, okay, so, there are only so many earthquake records that we have, and every earthquake's different. And so before we have an earthquake, we decide what buildings we'll do to a range of earthquakes, and we'll design for that. And so what we thought was going to happen in that first New Zealand earthquake is this black line. It's called a response spectra, and we design buildings according to this black line. We design for the accelerations on the black line because that's what we think they're going to do. Well, after an earthquake, if you have an accelerometer, which they had 7 of these in New Zealand, in Japan they have hundreds, maybe even thousands of them. But in New Zealand, in Canterbury, in Christchurch, in the CBD or Central Business District or downtown, they had these accelerometers. And so we have the actual record of the earthquake. And you've seen like seismographs in movies where it goes up and down like this. Right? That's how much the ground moves. This is something else. It's how much the ground accelerates. And so we get those records, we put it into our computer simulations, and then we can see what different story buildings will do in the actual earthquake. And so we recorded the earthquake, and it's funny, the record's different depending on where the recorder was. And so all these colored lines are all the different recordings that we found around town. And what's really, really interesting, you see this red line here? This is for north south, and I can't remember where this was. Um, Actually, I do remember because my job was to go find that recorder. They had lost it. They couldn't quite remember where it was, but it sent in the signal by phone, and we had it. And I ended up finding that recorder. It's a funny story for another time. But anyway, you can see at about 2.5 seconds or 25-story buildings, the actual accelerations were much, much higher than what the buildings were designed for. And so in this first earthquake, we were very suspicious that tall buildings, about in the 25-story range, would have more damage than we thought. And it's a long story for another day, but we suspect there were damages to these types of buildings. But remember those red, green, and yellow tags? These buildings inadvertently got tagged green because I believe the damage was hidden under carpet. And so we never actually got to saw them. And until today, I still wonder if those two tall buildings that collapsed in the subsequent earthquake were actually damaged in this first earthquake, and there's no way to ever know. Anyway, that's response spectra. Now, if you have time, why don't we continue on, and I'll just show you some pictures of the work I'm doing right now in Japan. And so after I observed the damage in New Zealand, I worked with that team from Japan, if you remember, and that led to more and more work there. And so now every summer and mostly every winter, I head over to Tokyo Institute of Technology, and I do work there on reinforced concrete buildings responding to earthquakes. And this is where I work. When I go there, this is Tokyo Institute of Technology. And this building was built before we knew everything we know today about earthquakes. And so it had to be repaired after the fact. And you see this tall rectangular piece of concrete there. That's a retrofit. And the bottom of this is hinged down to this little pin right here. And when the earthquake happens, this building will rock back and forth like this because this long vertical piece will keep it going like this. And so what it won't do is shake into an S shape or any other shape. And this actually makes it perform better in an earthquake. And they have these on all the buildings, and they all have these quotes on the bottom. And I like this one by Einstein. Information is not knowledge. And what we hope to transfer to you in your education, if you come here, is knowledge, not just information. It's a lot of fun working there. My buddy who I worked with in Christchurch has a nice lab. And so in this case, we're looking at this small wall, and we're going to move it back and forth, measure how it performs. And this is after the test. And there's a lot of these tests that they do. And the graduate students do a lot of the work. And so here you can see for the Japanese graduate students, this is the next specimen already put up, ready to test. And then the next morning, early in the morning, these tests take all day. Here you can see them at the computer testing it. They don't take a break even when it's cold. And so there they were working in the cold lab with some heaters. half of the students that I work with are Japanese, and the other half are international. And so this is Chanipa and Shreya, and they're international students working in Japan. But all the international students do their work in English. And so when I go there, I work mostly with the international students because we do all the work in English. Anyway, again, you can see that engineering work is international and it's just worldwide, especially something like earthquake engineering. It just affects everybody in the world. And so I hope you enjoyed our little talk about earthquake engineering. If you do come to the University of Wyoming, come see me. We can chat. Uh, we'll see. I'm trying to put together a course where we can maybe either in a winter break or summer break take 1 or 2 weeks touring around Japan, travel abroad course. But we'll see. It's kind of expensive and it's a lot of work to put something like that together. But maybe we could do that. Anyway, I enjoyed visiting with you. Have a great week and make the best of this time. It really is a good time to explore what engineering is. It would be better if you were here, but hopefully this gives you a flavor of the kind of research you could do in structural engineering.